Let's take a look at one more larger example. This time we've got 4 equations and 4 unknowns. We'll start by writing the augmented matrix, then apply Gaussian elimination, and finally backsubstitution. The augmented matrix is 3, 2, 1, minus 1, and 14, minus 9, 3, minus 3, 3, and minus 6, 0, 2, minus 1, 1, and 5, and finally 0, 0, 1, 1, and 1. To apply Gaussian elimination, we try to get non-zeros on the diagonal. To get our upper triangular form, we then need to get zeros beneath the diagonal. So we need to get rid of these non-zero elements here using elementary row operations. The first thing I'm going to do to get a 0 here is add 3 lots of row 1. So I'll have row 2 plus 3 lots of row 1. All the other rows will stay the same at this stage. So row 1 stays as 3, 2, minus 1, and 14. Row 2 then becomes minus 9 plus 3 lots of 3, or 0. 3 plus 3 lots of 2, which is 9. Minus 3 plus 3 lots of 1, that's minus 3 plus 3, which is 0. And finally 3 plus 3 lots of minus 1, which is also 0. Jumping over to the right-hand side part of the augmented matrix, we'll have minus 6 plus 3 lots of 14. That's minus 6 plus 42, or 36. We leave row 3 and row 4. And the reason we leave them is because their column 1 elements are already zeros. I don't need to do any work there. So the first column is already in upper triangular form. We can now move on to column 2. For column 2, we need a non-zero diagonal. We've got that. So we can move on to trying to make this element here a 0. And we'll do that by adding or subtracting a multiple of row 2. The multiple that we're going to work with is 2/9. And the reason we do that is because we don't want to take away a whole row 2, because that would be too much. We only need 2/9 of row 2 to get that back to a 1 and then multiply by 2 so that we can subtract the right amount and 0 our element there. All the other rows are going to stay the same again. Notice that because we subtract a multiple of row 2, which already has a 0 in its first column, the 0 in the first column of row 3 won't be changed either. That's good because we don't want to go back and have to work with column 1 again. Moving along though, 2 take away 2/9 of 9 will be equal to 2 minus 2, or 0, which is great because that's exactly what we want, but it is good to check it. Moving along, minus 1 take away 2/9 of 0 is not going to change. That's going to be minus 1. The same will happen for the next element. 1 take away 2/9 of 0 is still 1. And finally, 5 take away 2/9 of 36 will be 5 minus 8, or minus 3. So that completes our work on column 2. You can see that our upper triangular form is starting to take shape. We've got zeros below the first diagonal and now below the second diagonal. Our last piece of work is to get a 0 here in the third column. So what we're going to do is 0 that element using row 3. We'll say row 4 plus row 3, because 1 minus 1 is going to give us 0. All the other rows will stay the same. So we have 0 plus 0 is 0. And again, 1 plus minus 1 is 0. And finally, 1 plus 1 is 2. Moving to the right side of the augmented matrix, 1 plus minus 3 is minus 2. we've now got our augmented matrix transformed, or reduced if you like, to upper triangular form with all zeros below the diagonal, so we can move to the back substitution phase and solve this system. Starting with row 4, we have, looking back at what our variables were, a, b, c, and d, we have 2d is equal to minus 2, which implies that d is equal to minus 1. We can then go to row 3 and substitute that d value in. Row 3 tells us that we have minus c plus d, which is minus 1, equal to minus 3. Solving this, we'll have minus c equals to minus 2, or c equal to 2. Moving up to row 2, we have 9b equals 36, which can be rearranged to give b equals 36 on 9, or 4. And finally, row 1 is going to use all of those three values for b, c, and d. We have 3a plus 2b, or 2 times 4, plus 1c, or 1 times 2, minus 1d, which is minus 1, equals to 14. Cleaning that up a little bit, we get 3a plus 8 plus 2 plus 1 equals 14. Or 3a equals 14 minus 11, which is 3, which tells us that a is equal to 1. Okay. So our solution for this system, again a unique set of values for a, b, c, and d that will solve all four equations simultaneously, is a equal to 1, b equal to 4, c equal to 2, and d equal to minus 1.